We're now going to look at applications of derivatives and the fact that we're going to use what we've learned about derivatives as rates of change to help us figure out things or information about a function. Like, where is it increasing? Where is it decreasing? What are the absolute max and mins of the function? We'll learn about concavity. So we can put all this stuff together and be able to graph functions that we normally weren't able to graph before without calculus. So the first section in this new chapter, 4.1, is talking about the extreme values of a function on a closed interval. First thing that we need to recall is to remember what it means to be a maximum value or a minimum value. So we're going to let f be a function. And we're going to set some domain with a domain D. Then we can say f has an absolute maximum value on D, so on that domain, if at C, at a point C, if we can say the following: f of x is less than or equal to f of C for all x contained in our domain D. So that little funky E, it means contained in that set. Okay, that makes sense. Let's say you're looking at a graph. Basically, there's some value C here, some value up here. So that point, this is f of C. And if that's the highest value anywhere on that graph, that would be an absolute maximum value. So if I limit in my domain, maybe to here, so it would stop. Notice that this x equals C, my highest value on this graph is f of C. The y value is what the maximum is. The C value is telling me where to find it. So f of C is an absolute max. We would say that f has a absolute minimum value on D. Let's say at x equals B, if the following holds. Well, if it's a minimum, it has to be the smallest value. So f of B has to be less than or equal to f of x for all x on that interval D. If I was looking at the case that I just drew, if I was looking at the smallest value in this value here, it looks like it would be at the endpoint in this case. So it's possible that an absolute max or absolute min happens at an endpoint on an interval. If for some reason this graph was continuing forever, this would be a case where there was no absolute minimum, because this would be going down forever. But let me just draw something that does work. So in this case, notice there's multiple minimum values. We have one here and we have one here. We have one max. That would be a local max. It wouldn't have an absolute. But this one, notice, has the smallest value right here, f of b. So f of b would be considered, in this case, an absolute minimum value. So that's what it means to be an absolute max or an absolute min. Let's look at the following example, and let's look at it with different domains. So maybe let's say that we have some function f of x equals x squared. If I was looking at this, and let's say that the domain in here, first of all, was just all real numbers. If I graph that, right, that's just a parabola. This is a parabola, that has the vertex at 0, 0. And in this case, this graph does not have an absolute max. So there's no absolute max. But it does have an absolute min. So the absolute min in this case is 0 and occurs when x equals 0. Now let's say that we change the domain. Let's say instead we say the domain is between, how about, -1 and +2. Again, f of x is just x squared. So let's look at the graph of that. If we look at the graph of this, again, it's a parabola, but we need to figure out, we know where the vertex is, 0, 0. If I plug in -1 though into that function, my y value I would get back is 1. And if I plugged in +1, right, I get back 1. And if I plug in +2, I would get back 4. So it asked me to find the absolute maximum value in here. That absolute maximum value is going to occur at is 4. At x equals 2. And my absolute min hasn't changed, right? My absolute min is still here. I could say this point right here, this is actually a local. We'll talk more about the local min, actually max. Let's say though, that domain I gave you, same function, instead of being a closed interval though, maybe we have it opened. So maybe it's like at -1 and then closed at 1. So if I drew that function and I wanted to know where my absolute max and absolute mins are, notice that -1, that's an open circle because it's not included when I have that parentheses. this right here is not a max. We can always get closer and closer to this. I can always choose some value closer to -1 on the right, which would give me a bigger value that I chose over here, where the close point is a max. I would be actually have to be careful though. If I had said, how about this? What if I said open circle -2, closed 1? If I did that at -2, we got 4, right? But that's an open circle. Here at 1, we had 1. So here's a case where there's no absolute max. So right here, this is, if I could put an interval around it and it would be the highest point, but there's other values of x in here, right? In between here that are going to give me higher values of y. But I'm always getting closer and closer to this on this side. I'm never going to be stopping. I can always choose something that's a little higher, which is almost, that should be a 4. This again would have, though, an absolute min. So that brings us to an important theorem, which is called the extreme value theorem. And if we have some continuous function, and all these were continuous that we've been looking at, and we bound it within a closed interval, then it will have an absolute max and it will have an absolute min. And it's possible that it occurs at one of the end points. So let me put that down, what I just said. So if f is a continuous function, so it has to be continuous. On some closed interval. So we can label that as a bracket, A comma B bracket. Then f attains both an absolute maximum I call it capital M, and an absolute minimum. Little m on our interval AB. So basically, what do we have? Basically what I just told you guys. It's possible that this occurs on either A or B. Let's look at an example. Okay, this is where I'm surprised they teach it this way, but this is where we got to think about stuff that we've done before. Remember when we're looking at derivatives, if we had some maximum or minimum point, we knew that this slope here of our tangent line, or the slope at that particular value on the graph, these were equal to 0. And so when we're solving these, we want to find out where these are. These are called critical values. And this is our first derivative test. So the first derivative test, which says if f has a local, these are local, maximum or minimum value at an interior point, C of its domain, and our derivative function is defined, f prime is defined. Then f prime of C is equal to 0. Okay, so let's look at an example now. Let's say that we have f of x is equal to x squared minus 1. And we're looking at this between -1 and 2. So -1 is less than or equal to x, which is less than or equal to 2. And it asks us to find the absolute maximum and minimum values of each function on the given interval. Then graph the function and identify the points on the graph where the absolute extrema occur, and include the coordinates. So what we're doing is we're trying to find our critical numbers. We're trying to find the values where our derivative is equal to 0. So first thing you want to do is you want to find the derivative of your function. So that's not too bad. Derivative of x squared minus 1 is 2x. We want to set our derivative equal to 0. So 2x equals 0. That's going to be when x is 0. So this, by this test, is either a max or a min, local max or local min. Occur here. But because we've limited our domain and it's on a closed interval, it's possible that that absolute value occurs there. So really what you have to do is you need to plug in your n values of your inequality. So -1. We want to plug in any value which made our derivative equal 0. So 0. And the other n value of our point was 2. We want to plug this back into our original function and see what gives us the biggest value and which gives us the smallest value. And those are where absolute max and absolute min occur. So if we go back, and you have to plug it back into the original function. So f of -1. So plugging in -1, wherever I see an x in here, I get -1 squared, which is 1, 1 minus 1, that's 0. If I plug in 0, wherever I see an x squared minus 1, I would get 0 minus 1, which is -1. If I plug in 2, wherever I see an x here, 2 squared is 4, 4 minus 1 is 3. So the smallest value I get back, that's our absolute min. And the largest value we get back is our absolute max. So you're going to figure out what value set your derivative equals a 0. You're going to figure out and plug in those values into the original function and the endpoints into the original function to find the absolute max and absolute min. They wanted the point. That point here is going to be 0 and -1. And here, this point would be 2, 3. But knowing where the absolute max and absolute min is, and I know what this function looks like anyways, right? This is just by using algebra, this is a quadratic shifted down one. But we have a point at 0, -1. I know -1, 0. And I have one at 2, 3. So we can graph this. Which was one other thing they asked us to do. So they definitely get more complicated with more complicated functions. So maybe one more. So what about g of x equals negative square root of 5 minus x squared? And this wanted it between -√5 and 0 included. So it wants us to figure out the derivative. Before I take the derivative, let's rewrite this a little bit. So this is -5 minus x squared, all raised to the 1/2. So let's use the chain rule to take the derivative. We get negative, bring down our power, 1/2 of the inside, 5 minus x squared. Subtract 1 from our power, we get -1/2 times the derivative of the inside. Derivative of 5 minus x squared is -2x. So let's simplify. Negative and negative, that's going to be positive. We have a 2 in the numerator, 2 in the denominator. And we can bring this piece down to make it the exponent positive. So this is 1 all over the square root of 5 minus x squared. Well, this never equals 0. have no value of x, which would set that equal to 0. So really, only thing that we're worried about are n values. So let's plug in -√5 wherever you see an x and g of x. So g of -√5, this is equal to negative square root of 5 minus √5 squared, -√5 squared.
Professor, there's an x supposed to be in the numerator on g prime of x.
Oh, wait. Oh, you're right. Thank you. Thank you. So there is a value which sets that equal to 0. Right here. Trying to rush. Sorry. So we only really need to worry about when the numerator is equal to 0 in this case. We multiply both sides by that radical. The fraction will go away. And we get x equals 0. So I'm going to also have to put in 0 in here, but that's also the end bound here. So it wasn't anything in our interior value of our domain. And if we square a square root, -√5, that's positive 5. So I get this is negative square root of 5 minus that is going to become positive. So this is the negative square root of 0, which is 0. Where if we plug in 5, I'm sorry, if we plug in 0, so g of 0, I get this negative in front of my radical, 5 minus 0. So I just get -√5. So -√5 is a smaller number than 0. So this is my absolute min. Is -√5 at x equals 0. And then my absolute max, 0 is bigger than -√5. So this is my absolute max is 0. At x equals -√5. It's kind of like a semi-circle. Or a quarter of a circle is what it's going to look like, g of x. Okay, so that was kind of fast, 5.1. But really all you have to do is figure out when is the derivative equal to 0. And then test values on the end values of your domain. They're going to give you some closed interval. And you're going to have to test each value on the endpoint and any value which sets our derivative equal to 0 that is inside our domain. So for instance, if I had found x equals 3, set it equal to 0, I wouldn't have to worry about that because that's not in between and including -1 and 2. So that's 5.1.